Welcome back. This is Andy Schweitzer. Um, some of this is in review. This is basically our velocity and modeled velocity, how we model it. Some of this will be review from previous videos. Okay, so first of all, what is the difference between speed and velocity? Okay, so keep in mind, everybody knows what speed is. If you've been pulled over speeding, speed is a change in distance per change in time. Now, the distance doesn't exactly matter which distance you're going. Um, so at this point, we would say we take our, if we're traveling down a road, you could say, okay, from the starting point to the ending point, how fast are you traveling? If you're running the 100-meter dash, um, it's going to be distance would be your 100 meters. That's how the change you ran, and the time obviously would be the time that you ran that in. You would simply divide those two for your ratio between distance and time. With that ratio is then going to be your speed. Now, velocity is very similar. The only difference is that it adds an element of direction. So we're going to have not only a magnitude, but we're also going to have which direction it's going. So you'd have this ratio. You'd also have to add an added amount of which way are we going. We often refer to speed as what's called a scalar, pure value. Velocity is a vector, has a direction, and it has a magnitude. So both direction and magnitude. Um, if we were to graph this out, what would it look like? So, and there's a lot of models in which we could do this, but the simplest one is really using just graphing means. I'm going to go like, let's say like this here, and we can continue on if you want, but it looks something like this. This is called a position time graph. So the y-axis is going to be position, and the time is going to be in the x-axis right here. Now, it's important to understand that at this point, we are only doing two-dimensional movement. So that's spelled wrong, but either way, we're only going forwards and or backwards. Or we could be doing up, or we could be doing down. We're not going up and sideways. So we're kind of like a train on a track. We really only have a forward and a back going up and down. The third dimension, which is possible, it just takes a little more work, and we're going to start simple here. Okay. So a couple things here is that if we have, let's say, you're traveling from Appleton. So let's graph this out here. We're going to go from, let's go from Greenville, which is where we're currently located. So let's go Greenville, Hortonville area, Greenville. And, at that point, we're going to travel to Appleton. And then let's say we travel from Appleton to Oshkosh. And Oshkosh, we're traveling down to Milwaukee. Right? Now, let's just say that you're traveling from Greenville, okay, to Appleton, and this is more residential, a little harder going here. Let's say we travel this distance, which is, let's say it's 12 miles, and in this case, let's say it takes us 30 minutes. Okay, we slow down, hit a little bit. It's not. It's a little longer than you might think. Actually, it probably should be let's just say 30 minutes. Um, Appleton to Oshkosh. Okay, again, this is about 15 miles, and let's say it took us only 15 minutes. And then let's say Oshkosh to Milwaukee. Let's say this is another, I don't know, 75 miles. And let's say this only took us 60 minutes. So in this case, if we're going to graph this out, one, time our unit is going to be in minutes, and our position would be in miles. And we could even say at this point, we then travel back to Greenville, okay, and let's just say we take a plane, all right, travel the same distance, let's say it's 75, so 85, 90, 102, so this is a total of 102 miles. So let's just say we go 102 miles back, and we do it in let's go 1 hour, 60 minutes. All right. So now, obviously, on the screen here, it's not easy to do exact values as far as distance-wise spatially, but we'll do our best. So on this thing here, we're gonna go miles. We'll go. Let's go. All right. So we're gonna go 20, 40, 60, 80, 100, and let's go equal out here as well. Okay, and so this is going to be, we want a total, let's say, of 2 hours. So we'll go 30 minutes. Let's go 30 minutes, 60 minutes, 90 minutes, 120 minutes, and let's go 180 minutes. We won't get that far, but all right. So in the first 30 minutes, we only travel 12 miles. So we go over 30 minutes, and spatially have to be about 10, so we'll go right about here. Okay, this is our first mark. And then from there we travel another 15 miles in 15 minutes, so half of that time. Right here we go from another 15 miles. So at this point we've gone a total, I'll put that in parentheses here, 27 miles, so close to 30 miles. And that puts right about here. So we're going to go half our time right there and right about here, close to 30, right in the middle. All right, oh, like that, right about there. All right. Now you notice here, first you notice that our slope is starting to pick up a little bit. The slope represents the y-axis divided by the x-axis. So the slope, or the derivative, is equal to y over x. And you can say even the change in y over the change in x. And that's our slope. So next, we're going to go the 75 miles, which is going to put us right at around 100 miles. So we're going to be all the way out to here, 80, 30, 60, that's just time-wise, so miles all the way up here. So we're going to be another 60 minutes. All right, so that puts us halfway, 30, 60, about an hour right here, and we're going to be all the way out to here, right there. So our slope has drastically picked up at this point. Okay. Now, distance-wise, displacement, okay, we got a total of 102 miles away. So we're right here. This is 102 miles. All right, but now we start heading back, and it only takes 60 minutes to travel back. So right here is our 30 minutes from there here. So right now we're gonna have to put a point all the way back to here, and there we go. All right. Now this is your typical graph. Now in this case, we could do an average velocity, okay? Average velocity is different than an instantaneous velocity. Let me give myself a little bit of room here so we can talk about average versus instantaneous. Now, my average velocity, okay, average in this case, is going to be the total, different change in your distance traveled divided by your change in time. Now, in this case, we traveled to Milwaukee and back. We marked that out as being about 102 miles there, 102 miles back, so that's 200 and 2 miles divided by what appears to be total time-wise. We got 30, 15, which is 45, plus another hour and 45 minutes. And then we had another hour on there coming back, so 2 hours and 45 minutes. All right, so that would be 120 plus the 15 plus the 30. We got 5, 3, 4, 5, 6, and then we have 165 minutes. 165. All right. Now, in this case, this is our average. Now, in this case, our average velocity. Okay, well, average speed, you should say. Now, if you want to know the exact speed at that point, now because this line is straight, our velocity is the same across. So I could easily get the slope of this line, and at that point I would try and find some convenient marks across here, and I'd want to try and find, let's say, looks so good, some sort of a rise over run on this thing. Pick out 2 points, and okay, rise, run, mark out on the side where this thing is, and this will give me my rise, how much distance traveled. This is my y component, and then from here I can get my time, so my x component, and then you take your y component divided by your x component, and this will give you your average velocity over this point. Okay. Now, to get your actual pinpoint velocity, this is something that we don't generally do because it requires a little bit of calculus. This would be referred to as your derivative or your actual slope at that exact instantaneous point. But if we did this same exercise, you got the distances smaller and smaller, or if we can say that the slope is consistent over the entire area, we could say right now this slope over this larger area equals the slope at that point because it's not changing. So to find individual instantaneous speeds, we need to find the individual instantaneous slopes at those points. So average over a larger time, instantaneous, we're looking at a relatively smaller time. A few things to notice that distance-wise, displacement-wise, we ended back at the same point. This is start. This is the same place we started at. Just looking at purely displacement. Other models of velocity. Okay, let's look at an alternate model. You will see some things like this in case where they might use a picture. Okay, you could have a person. Let's just say we have a line here where a person's running. Okay, so Mr. Stickman is standing here, and let's say every second, we're going to take a picture. So we'll say, and I'll just have, so because the time is consistent, I can have consistently spaced marks. This is time, okay, and let's just say it's in seconds. It doesn't really matter what the time is. But if this person is just strolling along, then the distance traveled, this is considered my distance. And if he's traveling very slowly, then we would expect the next picture, the person would be relatively close. Let's just say the person now is located right here. Okay? And next second, or next time frame, he's right here. And every single time, he's equally spaced. That means for a consistent time picture every second, he has an equal distance between him. That means this guy is traveling at a consistent speed. If we saw this person traveling faster, well, then we'd see, okay, a larger distance between him. Okay, bigger distance, same amount of time. Remember, a picture is taken every second. So every time you see a picture, it's a second. And then the next one, same thing. There he is. So now, at this point, he's traveling, let's just say this is the same distance, okay? He's traveling still a consistent speed, but because it's a larger distance, he's traveled a larger distance. Now remember, speed is distance per time. And our time is 1 second. He's traveled a larger distance, and that's 1 second. So compared to my first section, he's traveling relatively slowly. my second section here, traveling relatively fast. So at some point between right here, this person has decided to accelerate from a slower speed to a faster speed. And again, if I were to show the next one even farther, this person would be traveling even faster. So at this point, the last section, this person accelerates to a new speed. Occasionally you might see something that's creating dots. You know, dot, dot, dot. And as long as the dots are in consistently spaced, we say we have a constant speed for a given time. If you see dots that are faster or farther apart, they are traveling faster. If you see dots that are slower, moving slower, and all of a sudden they get wider, this thing is accelerating. It's moving faster. If you see something where you have bigger dots and all of a sudden they become closer together, this thing is slowing down. It's traveling a smaller amount of distance per time, assuming that the dots are being collected at an even time spacing. So these are some of the models we use to show distance and distance versus time. Inside this, of course, we're starting to see aspects of acceleration. Of course, acceleration is the velocity final minus velocity initial divided by your change in time. This can sometimes be represented as the change in velocity over the change in time. We see this as being either accelerating or decelerating, either way up. To accelerate, let's say, over this range right here, okay, we have a positive acceleration. We're increasing in acceleration. Whereas, let's say, in this here, we have a negative acceleration. We're slowing down in this region here. Okay? One more thing I'm going to mention about this acceleration and velocity is that because velocity adds an element of direction, we often say on a scale, if a person is moving, let's just say, it doesn't matter how you model it, use either one of our models, but if we're moving, let's say, to the right, okay, we would have a positive velocity. If we move to the left, okay, we have a negative velocity. Therefore, if we were to accelerate to the right, then we would have, again, a positive acceleration. If we would accelerate to the left, we would have a negative acceleration. And acceleration just means we're increasing our velocity in that direction. If just a quick little example, if I were to roll down a hill in this direction, I would have a positive velocity in this direction, and I would have a positive, at least let's just say at the very top here, okay? In fact, let's redraw this a little bit here to give you a better example of this. You start at the hill, top of the hill. You're not moving very fast, okay? I'm just going to draw this hill out here. Ooh, steep one. So let's just imagine you're moving very slowly, and eventually you start down the hill, and the length of the line means you're traveling. That's the length of the line represents the magnitude of your acceleration. And eventually you start to slow down, until you stop, get up. Mr. Slider gets up, and he walks back to the top hill and starts again. So along this way, a unique item happens right here. We start slowing down. So we're going to have a positive velocity all the way along here. We're traveling in a positive direction. But my acceleration is going to be positive in this direction. Positive. I'm gaining speed until at right here. Now I have a net slowing down. So my acceleration is now negative acceleration, negative acceleration, negative acceleration until I stop. So keep in mind, if I'm traveling in the positive direction and I have a positive acceleration, you can see that person is speeding up. If I'm traveling in the negative direction and I accelerate in the negative direction, you'd also see this person, let's erase that negative there. Should erase that, never mind, doesn't want to do that, there it goes. A negative acceleration, you'd see the velocity overall speed up in that direction. Or you could see a situation where the acceleration, if we're traveling a velocity in this direction, positive, but the acceleration is fighting against it, negative, you'd see this person slowing. The velocity would be diminishing and eventually come to a stop, and then could potentially go backwards. All right, we'll stop there for today. Thank you.